Hello, welcome to our little exam review video. I'm going to spend this time working through the practice final exam. So I've got a version printed here. Let's walk through it. So number one, it's a true-false problem. So determine whether the statement is true or false. The limit of f of x as x approaches a describes what happens to f of x when x is near but not equal to the value a. Well, that is just true. That is the definition. This is a big part of the definition of the limit. What matters is what's happening as x is approaching a. So, yeah, that's just true. All right, for number two, and we'll see this in action here, we are looking for limits. So, first up, what's happening as x approaches -3? Right, well, here is the x value, -3. And again, what matters is where you're headed. Notice that as we get close to x equals -3, we're headed to this point right here. Now that's not the literal f of -3, but that's not really what matters with the limit. It's where are you headed? So we're headed to this height, which is height 2. This is height 2 here. And yes, I'm saying that this exists. So part B, the limit as x approaches -1. Right, well, here's the x value, -1. And notice that there's disagreement depending on the direction. So the left-handed limit is -1, that's this height here. But the right-handed limit is 1. So because there's this disagreement, that means that the limit does not exist. They have to be the same coming in from both sides. So now we're going to solve limits without a graph, but using our algebraic techniques. Notice that if you try to plug in x equals 5, you're going to run into problems. You'll get 0 over 0. And that tells you nothing. So instead, what you want to do is factor whatever polynomials you can. So x squared minus 25 can be factored as x minus 5 times x plus 5. And now we've got some canceling. So now this is the limit as x approaches 5 of just x plus 5. And now we're free to plug in 5 for x. No problem. We get 10. So yes, this exists, and it's 10. Okay, let's try another one. So similar thing, you want to factor the polynomials because if you just try to plug in 5, you'll see it's not going to work. Right here we'll get 25 plus 20, that's 45, then minus 45, so that's 0 over 0. Okay, so we're going to have to factor again. So what does that numerator factor into? The denominator we've already seen is x minus 5 times x plus 5. Well, two numbers that multiply to 45, 9 and 5 are a pretty good combo. One of them needs to be negative because they multiply to negative 45. So that means if I do plus 9 and minus 5, that'll work because for the x term, we'll get 9x and minus 5x, that is plus 4x. So the x minus 5s cancel. And now we have a new limit, or it's written in a new way, of course. It's the same ultimate answer. But now we're free to just plug in 5 for x. No problem. Get 14 over 10, and that reduces to 7/5. And that's what they're looking for, either an integer or a simplified fraction. So 7/5. Okay, average rate of change. We're asked to find the average rate of change of the function on an interval. So to remember this formula, think of this as the slope of what's called secant lines. Like say this is A and B, and we're looking for the average rate of change on this interval. Well, you connect the 2 points using a straight line. That's called the secant line. And it's the slope of that line that is the average rate of change. So think rise over run. It's not even a limit in this case. That's for instantaneous rate of change. But for average rate of change, you don't need a limit, so you can eliminate part D, part B. And it's not going to be plus because you don't use that in a slope formula. It's rise over run. So difference in y values divided by difference in x values. So those will be subtractions. And my picture here wasn't perfectly accurate. Of course, I just made it up. But this is the slope of the line that connects the 2 points. Oh, and then they're asking for what is it? Okay, we can do that. Let's solve it up here. F of 6 minus f of 2. So that will be 24 plus 1 inside that square root. And then f of 2 is square root of 8 plus 1. That's over 4. So square root of 25, that's 5 minus 3 over 4. So 2/4 or 1/2. All right, next, number 6. So we're told the position of an object that's moving in a straight line. Find the instantaneous velocity when t equals 3. Well, instantaneous velocity, velocity is rate of change of position. So this is instantaneous rate of change. And whenever you see that, as opposed to average rate of change, think derivative. The instantaneous rate of change, that's how fast you're changing at an instant at a point. That is the derivative at that point. So we just need to find the derivative. That will be velocity, s prime of t. So we're free to use power rule on this. So bring that 2 down, 2 times 4, t, 8t, minus 6. The negative 10 term will go away. Its derivative is 0. So this is the general function for velocity, but we're asking for it at time t equals 3. So we just have to plug in 3. So s prime of 3, 8 times 3 minus 6. So that's 24 minus 6, 18. Okay, next. Find the derivative. Okay, this one's kind of nice, just a power rule. So dy dx, remember that's notation, just means the derivative of y with respect to x. Like x is your main variable. So for x cubed, you bring the 3 down, that 3 exponent down, and you subtract 1 from the power. Okay, next, with the 2 will come down. So that is minus 34. Now just x to the first power. 63x, its derivative is just 63. And the plus 6 won't matter. So here, I don't need to write it again. That's the answer. Well, number 8 here is actually just a power rule as well. It may not look like it at first, but you have to recognize that the square root of x is x to the 1/2. And then you're free to apply the power rule. So dy dx, bringing that 1/2 down times 6. So when you subtract 1 from 1/2, you get negative 1/2. And here the 2/7 comes down times 7. That'll be x to the negative 5/7. When you subtract 1 from that 2/7 exponent. Okay, we get a little bit of simplifying here. 3x to the negative 1/2. Here, 7s will cancel. Plus 2x to the negative 5/7. This is how Pearson gave their answer, so no need to go any further from there. It turns out number 9 is power rule as well. We just need to rewrite as 3x to the negative 6 minus 4x to the negative 1. This is perfectly fine for power rule. So dy dx, bring the negative 6 down, times 3. Notice when we subtract 1, we're getting further negative. That happens. Negative 1 comes down here, times 4, x to the minus 2. So we get negative 18, x to the negative 7. This will be a plus 4, x to the minus 2. And if we want to, we could go a little farther Pearson actually gives their answer like this, though I think what we wrote would be fine. But this is how Pearson did it, so I'll write it. Same thing. Now we're getting into the derivative rules, besides power rule, that is. So product rule. We are not allowed to just take the derivative of each individual piece here. It's a process where you take the derivative of one of them at a time. So dy dx is, first you leave x plus 1 alone, then times the derivative of 9 square root of x. I'm rewriting that now. Plus 2. Then plus, the other way, I take the derivative of x plus 1, then times 9 square root of x plus 2. Okay, so what happens? We get x plus 1 times 9 halves x to the negative 1 half plus, well, derivative of x plus 1 over here is just 1, times 9x to the 1 half plus 2. Okay, so we have to distribute this part, multiply that out. When I do x times x to the negative 1 half, remember you add the powers. So that's x to the 1 times x to the negative 1 half. So that's 1 minus 1 half. And we've got this 9 halves coefficient here as well. So 9 halves x to the 1 half. Okay, plus. Now this guy times 1. So just 9 halves x to the negative 1 half. Plus 9x to the 1 half. I'm going over here now. Plus 2. So the only thing left is that we can combine like terms. Got a couple x to the 1 half terms. So those can combine. 9 plus 9 halves. Well, you want to write them as a common denominator to get a nice exact answer. 9 halves plus 9. To combine these like terms here, we want to rewrite 9 as 18 over 2. Same thing as 9, but now these have the same denominator. And then 18 plus 9 in the numerator gives us 27. 27 over 2. So I'll probably end up erasing most of this stuff to save room, but our answer is 27 halves x to the 1 half. Okay, I need to start making space. Then we have an x to the negative 1 half term, so plus 9 halves x to the negative 1 half. And don't forget the plus 2. On to number 11. Now we have a quotient rule problem. So remember, when you're taking the derivative of a quotient, that is with division, it's not just, okay, this derivative divided by this derivative. There's a full rule. Think low d high minus high d low over low squared. So sorry. Just trying to discern if another train's coming. So low times d high ddx of 6x plus 5 minus high d low. Okay, then that is over low squared. All right. So next. Whoa. Now we start taking those derivatives. So we've got here, let's write down here, x to the 1/2 times 6. So let's just write 6x to the 1/2 minus. Now we've got to distribute here. Might want to take this part a little slower, actually. Here I took the derivative of x to the 1/2. And that is over x. All right. So now I can do a little distributing up here. So we get a 3 because of this 1/2 times 6. All right, then we have x times x to the negative 1/2. So we add those powers. 1 minus 1/2. Okay, then here we have a minus 5 over 2. X to the negative 1/2. And that's all over x. So what can I do further? I can combine these like terms. Got a couple x to the 1/2 terms. So together they make 3x to the 1/2. And that's minus 5/2 x to the negative 1/2. All over x. And if I want, over here, I can even go ahead and write this as 5 over 2 square root of x. So I'm doing this to demonstrate that we don't really want to have fractions left over up in that numerator. So I want to bring this stuff down. And that's how Pearson prefers to do it. So I'll show you that. The only downside is that when I change this denominator to 2x root x, okay, that'll be nice for that term over here. but it will make an impact on the other one as well, because this is the same denominator for the whole fraction. All right, well, think of it as, just in terms of the numerator, to get rid of this 2 root x, I'm quote unquote multiplying by 2 root x. So the same thing we will want to do here to make this balance out. So multiply 3x to the 1/2 by 2 root x. So I'll just be a little more specific, show my work here. Times 2 root x, and that's minus 5. Well, x to the 1/2 and root x are the same thing, right? So this becomes 6x minus 5 over 2x square root of x. That's Pearson's preferred way of simplifying. So how about I write that in the answer box? Then we'll have some erasing to do. Number 12. Find the derivative. Okay, so this is a chain rule, you can tell, because you have a function inside another function or process. So keep track of what is outside versus what is inside. You take the derivative of the outside part first, and then you multiply by the derivative of the inside. So the outside is this 4th power. So we're going to perform a power rule on that. So bring the 4 down, and then you leave this inside part the same. To the 3rd power. And now you multiply by the derivative of the inside. So I won't actually do that quite yet. Okay, so we get 4 times this whole polynomial cubed times this derivative. It'll be a 24x cubed minus 12x, and that's it. So that's the answer. I'm not going to write it again. Right, number 13. Find the derivative. Okay. Well, clearly there's some quotient rule involved because this is a big quotient division. We've got e's involved now as well. So we'll need to make sure we can handle those. Notice there will be a bit of chain rule because of the e to the 9x. You've got that 9x in there instead of just e to the x. Well, the big thing that's happening is the division. So that's going to be our main focus. It's an overall quotient rule. So dy dx equals, you got low, d high. So what's the derivative? E to the 9x. That is itself. The outer derivative is the e part, and derivative of just plain old e to the x is itself. So this is the outer derivative, part of chain rule. And then you have to multiply by the derivative of the inside. That is the derivative of 9x, which is 9. Plus, now we have to take the derivative of e to the negative 9x. Well, again, that's going to be itself times the derivative of negative 9x. That's negative 9. So that is low d high minus high d low over low squared. So that's low d high minus high d low over low squared. Now it's just a matter of simplifying. Okay, so we get 9x e to the 9x. And okay, don't forget to distribute this x again right here. And so I'm writing minus because of this negative 9. Minus 9x e to the negative 9x. Okay, then minus this whole thing. So minus e to the 9x and minus e to the negative 9x. All over x squared. Okay, and that's pretty much all you can do for simplifying. Pearson, they had you factor out this 9x here from those two terms. That's fine. So let's do that. Here, I'll write it over here. Oh, goodness. Okay. Um, I don't have enough space. All right, I might have to erase this in a bit. There we go. So I just factored the 9x out of these two terms. That's it. Okay, and then they decided to group these together. So I guess that's factoring out this negative. Okay, you can do that. Whoa. So if you factor out the negative like that, then you're writing those as a plus. Well, that's the nicest way to write it. But I personally wouldn't have a problem with the other way. Okay, next. Find the derivative of the function. Okay. So, since this is a video, I'm going to erase this stuff now. You can go back if you need to see that. But we need the space. Okay, there are a couple ways to do this one. You could do chain rule within chain rule, right? Because we have ln of a square root of something inside the square root. So it's like this triple composition. That's doable just using chain rule, but I can show you a better way by using log rules. So I'm not even taking the derivative yet. I'm just going to rewrite this function. Rewrite that as x plus 13 to the 1/2 power. And there is a rule with logarithms where when you're taking the log of an exponential, you can take that power and just move it out front. So this is the same thing as 1/2 times ln of x plus 13. Now, I haven't even started taking the derivative yet. I just rewrote the original function, and this is way easier. So now we take the derivative. So remember, derivative of plain old ln of x is 1 over x. Well, now we have x plus 13 in there. So this is a chain rule. It's 1 over that whole x plus 13 times the derivative of x plus 13. That's chain rule. Well, this turns out to be just 1. So didn't really matter, but you just want to be able to understand what I did. So really, these two come together, and we can report our answer as 1 over 2 times x plus 13. Let me double check something real quick. Okay. Number 15. We've got a graph here. We want to find the locations and values. So that's x values and y values of all relative extrema. So that's like local maximum or local minimum. Okay. So this is a bit of a funny way to do it. So the values they've told us already, that is the y values. Right, well, if we look at our graph here, and I hope that my drawing will stand out enough, we can see, okay, that's a high point there in its little neighborhood. That's a local maximum. And this right here is a low point. That's a local minimum. Or relative maximum, relative minimum, same thing. So the 0 one is right here because that's the y value, that's the height. So 0 is 0 here. That is a relative maximum. It's a high point. Okay, so I just filled that in over here. It's a maximum at x equals 1. Now this other point here, that is y value of -1, so that's the value. That's a minimum. It's a low point. So we have a relative minimum of -1 at x equals 3. That's the location we're at, the x value here. All right, so no fancy first derivative test or second derivative test. Just looking at the graph. Number 16 is a great problem. Notice it's asking, or it's telling us rather, the graph of f prime of x, that is the derivative. So this graph is not of our main function, it's the graph of the derivative. So based on that, we want to find the relative extrema of f. That means we're going to have to use this picture in a creative way. Right. Well, how did we classify relative maximums, relative minimums? We did that by finding critical points and then using either first derivative test or second derivative test. And spoiler, we'll want first here because that's what we have. We have the first derivative. Okay, so I want to find the critical points and then classify them by first derivative test. So, what are critical points? Well, they are the candidates for these relative extrema, local maximums, local minimums. They're the candidates for that. And maybe I can write over here. Critical points are critical numbers. That's just the x value. Remember, they are when the derivative is 0. That's the main thing to look for. But also, if the derivative is undefined or does not exist. Also, endpoints, those are a place to check. Could be a local max or local min. Well, the only thing that applies here is this first one. The others are not applicable to this problem. Right, this graph here, you can plug in any x and it'll work. And there are no sudden sharp endpoints either. So, where is the derivative 0? Well, that's the graph that we're dealing with, the derivative. So that would be where we cross the x-axis. So those are my critical numbers, x equals -4 and x equals 2. So those give us the possible candidates for local maximum or local minimum. So now we use the first derivative test to classify these. So I'm going to analyze the sign of the derivative, that is, whether it's positive or negative. I have a little x-axis here. So -4 and 2 we're concerned with. And now to classify these, we need to determine whether we're positive or negative on each side of these. So, for example, with -4, when I'm to the left of -4, notice my graph is negative. The derivative is negative. So we're negative over here on the number line. Well, when we are between when we're between -4 and 2, the derivative is positive up here. But then when we are to the right of x equals 2, the derivative is negative again. We're below the x-axis. So based on the first derivative test, think of it like f is decreasing and then increasing around -4. So that means it's like a dip. So that will be a local minimum. Well, around 2, I'm first increasing and then decreasing, dropping off. That'll look like this, a maximum. So I think something got cut off here when I printed this. Yeah, because C is supposed to be both, according to what I'm seeing here on the answers. So we have relative minimum, let's just write down here. You shouldn't have this problem on your end. It's because I printed this off. Relative minimum, okay, at x equals -4, and relative maximum at x equals 2. So I believe that's supposed to be C, but looks like it got cut off. Because notice that C and D are the exact same here, the way it's written. So yeah, there's something wrong with that. Okay, whatever. So number 17. Find the open intervals where the function is concave upward or concave downward, and find any inflection points. So when you see any of these words like concave upward, concave downward, inflection point, that all has to do with the second derivative. So here they're first wanting you to find the first derivative. That's just because you need it anyway to find the second derivative. So the first derivative we will write is -2x minus 11. Then f double prime is the derivative of that, just -2. Right, so we'll fill those in. So that helps. So f double prime is -2. So it's just that value everywhere, no matter what x is. That means the entire thing is concave downward because the second derivative is negative everywhere. Okay, so we can eliminate some things here. Yeah, that would be C. Concave downward on the interval from what's everything, -infinity to infinity. Never concave upward. Okay, well, that makes this next part kind of nice. We can be for sure that there are no inflection points because that is where the concavity changes. Like you switch from concave up to concave down, or vice versa. That's an inflection point. So in that case, you would want to find out, where is the second derivative 0? Well, that doesn't happen here. It's -2 no matter what. But hypothetically speaking, you would want to find where is the second derivative 0, or perhaps undefined, and then check around those points. If the concavity changes from one side to the other, then you have an inflection point. But there are none in this case. We're just always concave down. Okay, next, number 18. Absolute extrema. So, a relative extrema, or that is local max, local min, that is asking whether you are a high point or a low point within your little neighborhood. Absolute means that we're talking about the high and low points on the whole interval. So that would be on this domain 0 to 3. So the way that we find those, we still need to find critical points because, well, our absolute extrema will always also be relative. That's because if you're the high point on the entire interval, then you're also going to be the high point in your little neighborhood. So we still look for the candidates of relative extrema so that we can find the absolute extrema among that list. All right, why don't I make myself smaller here? Because I'm worried I might be blocking stuff out at some points. There we go. Okay. So we still need to find critical points. We will need the derivative. Let's find that here. F prime of x. Well, low d high minus high d low. This is a quotient. So low d high, that's -1. It's the derivative of 1 minus x. Minus high d low, that's 1. Over low squared. Okay, let's simplify that. So the x's will cancel. See, because I have a negative x here and a double negative, so positive. So the x's cancel. And what's left? A -1 times 3. So -3, then -1. So -3 minus 1, that is -4. I just wanted to save a little space here, so I didn't write all that work. All right, so -4 over 3 plus x squared. Let me just double check that math real quick. Yeah, looks right. Okay. So, are there any critical points? Any critical numbers? So, first up, is the derivative ever 0? The answer is no, because this numerator is never 0. It's always -4. So that'll never be 0. Okay, so we can rule that out. Will this ever be undefined? Well, yes, but wherever it's going to be undefined, the original function also is undefined, so it doesn't really matter anyway. Right? We are undefined when x is -3, but so is the original function. So we're not going to have an absolute maximum, absolute minimum there. So yes, technically, the derivative is undefined when x is -3, but it doesn't matter because so is f. Okay, so that's out. Well, the only other thing for critical points is, are we at an endpoint? And the answer is, well, yes, we have a couple of those. We are on a closed interval from 0 to 3. So the critical numbers are just those. Those are all we have. All right, so now what? Well, these are the candidates for our absolute extrema. Okay, and we know that these absolute extrema will exist. Why? That is extreme value theorem, EVT, extreme value theorem. The absolute extrema exist on the interval from 0 to 3 since f is continuous on this closed interval. Right, interval. So we know they'll be on here. And we know that, well, if they're going to be on here, it's got to be one of those points at 0 or 3. So we've pretty greatly narrowed things down. Right? So what you do, plug in 0 and 3. Let's make a little table. So 0 and 3 we plug in to f of x. See whichever one gives us the big number, which one gives us the small number, and those will be our absolute maximum and absolute minimum. So here's f of x. If I plug in 0, I get 1/3. And if I plug in 3, let's write this out. I get 1 minus 3 over 3 plus 3. So -2/6 or -1/3. All right. And that's lining up with my answer key, so that's good. So just to fill this in, notice that we have specific instructions to round to 2 decimal places. So they don't want us to give the fraction 1/3. The absolute maximum, that will round to 0.33, which occurs at x equals 0. And the absolute minimum, that's the low one, is at -1/3 or -0.33, occurs when x is 3. And yeah, we would have to fill in both of those a's there. So it's because of extreme value theorem, by the way, this EVT here. That's why we know that both of these answers are A. That the absolute max and the absolute min both exist. Because the function f of x is continuous on our closed interval. The only problem point would be -3 for x. That's not on our interval at all. So got it. All right, find the equation of the tangent line. I'm going to erase some of this old stuff here. Give myself a little space. Find the equation of the tangent line at the given point on the curve. All right, so here's the curve, x squared y squared equals 4. And we are looking at the point on that curve, -1, 2. All right, so to find a tangent line for the equation of a line, we need two things. We need a point, which we have, and a slope. So this point here is a point on the curve. Since this is a tangent line, it's also going to be on that line, right? That's the purpose of a tangent line. it touches the curve at that point. Here's just a rough sketch. All right, pretend that's a straight line. So we have a point, we just need the slope, really. Well, slope comes from the derivative dy dx. The problem is that this is not just a simple curve y equals some function of x. Instead, this is an implicit relationship between x and y. Well, we still want dy dx, but we're just going to have to do implicit differentiation to get there. So you take d dx, the derivative with respect to x of both sides, and when we do this, dy dx will naturally come out. So I'm taking the derivative with respect to x, but remember that y depends on x, so it will be affected by this. That means I have to do a product rule here. So x squared times the derivative of y squared, start there. Well, you take the derivative like normal, 2y, but then because this is a y and not an x, you have to multiply by dy dx. Really, that's chain rule. It's like I'm multiplying by the derivative of y, that is the inside function. So I just did x squared times the derivative of y squared. Now we take derivative of x squared times y squared. And d dx of 4 is 0. And now we could do algebra to solve for dy dx. That's actually really not all that necessary in this problem, at least not yet. Because really, I could just start plugging in this x and y value now. And that might make life a little easier. So we plug in -1 for x times 2, y is 2 at this point. 2xy squared, that's 2 squared. Okay, so now I can solve for dy dx at this point. That will be the slope of our tangent line. Okay, so I'm going to have to go down here. I can erase it later. Notice this will be a 4 dy dx, positive 4. Here, I'm going to have a -8. We've got the -1, and then we've got a 2 times 2 squared. So if I move that -8 over to the other side, that'll be 8. Divide by 4. We get dy dx is 2. And I'm really saying dy dx at this point, -1, 2. But that's what matters. So this is the slope of my tangent line, 2. So the slope is 2. My picture's definitely wrong. That's okay. That's just a rough sketch. So now the equation of the tangent line. So point slope form, because we have a point and we have the slope. It's y minus the y value of my point, that is 2, equals slope 2 times x minus the x value. And then we will need to rearrange this because they are wanting a y equals form, that is slope intercept form. That's just some algebra, right? I can distribute that 2 and maybe simplify this a little bit. Here, this is 2 times x plus 1, or 2x plus 2. So that is y minus 2 equals 2x plus 2. So to get y, I just add 2 to both sides. So now that goes in the answer box, y equals 2x plus 4. All right, I'm going to have to erase a lot of this, but you've got it on video. Number 20. Got a manufacturer of handcrafted wine racks, and we have a cost function of X units per month. Okay, right here, the C. So how fast is the cost per month changing? So that's a rate, right? How fast? That's a rate. So some sort of derivative with respect to time. How fast is the cost per month changing when production, that's X, is changing at a rate of 10 units per month and the production level is 80 units? Okay, so this is a related rates problem because we're asking about a rate and we have two variables involved, C, the cost, and the production level, X. They're going to have a relationship with each other. They're derivatives. So time t is the main variable here. So I want to take this relationship that I have and take d dt of both sides, derivative with respect to time. A plus 8,000, that 8,000 is going to go away. Right? This is implicit differentiation still. The derivative of cost with respect to time. That's what the problem's asking for, by the way. Is, all right, we take this part, bring the 2 down. So 0.4 x to the first. But remember, my main variable here is time. So I need to multiply by the derivative of x with respect to time. So this sets up the relationship between the rates, the related rates. And we can see based on the question, so how fast is the cost per month changing? We're asking for this part, dc dt. Well, for these parts, we're told specifically we're concerned about when the production level, X, is 80 units, and when the rate of production, dx dt, is 10 units per month. So we just fill in those details. Right, so when production level is 80 units and production is changing at a rate of 10 per month. right? So now what's going on here? Well, first, costs, are they increasing or decreasing? Well, we can tell that they're increasing because of the rate. The rate is positive. This is a positive number. So it's increasing. And the rate, you just have to multiply this all out. I would start with the 10 times 0.4. That just moves the decimal over. 4 times 80. That is 320. So we didn't even have to round in this case. That is exact. Great. So now we are on to integration. All right. So this is an indefinite integral. Notice there are no numbers here, no bounds of x. So that means we're finding the antiderivative, or really all antiderivatives of this function. This is just a polynomial. So we apply the power rule, but it's backwards from the derivative power rule. So in this case, you add 1 to the power, then divide by that new power. So let's write this over here. We've got 3 times x cubed, I've added 1, over that new exponent, 3. Notice these cancel. Then we've got the 6x term. That's minus 6. That'll be x squared divided by 2. And little canceling there as well. The plus 3, that will become plus 3x. And do not forget plus c, because this is all antiderivatives. So you could have some constant there. So final answer would be x cubed minus 3x squared plus 3x plus c. Number 22. All right, this is actually a power rule as well. When you rewrite this integral, 15x to the 1/2, you don't need to write the root 7 any differently because there's no x involved in that. That's just a constant. So I've got the 15, and then I add 1 to the exponent, so that's x to the 3/2. Then divide by this new power, 3/2. Don't let this square root throw you off. That's just a constant, square root of 7. So we get root 7 times x plus c. Okay. Little bit of simplifying we can do here with the 15 divided by 3/2. Think of it as 15 times 2/3. Same thing. And then you get a little canceling here. Yes, that's a 5. So we get 5 times 2, 10. So 10 times x to the 3/2 plus square root of 7 times x plus c. And we'll just leave it in that form. That's good. Okay, number 23. We want to find this antiderivative. Well, this is also power rule as well. You just need to rewrite a sixth root as x to the 1/6. Okay. So you will add 1 to the power. That's 7/6 divided by 7/6. Okay, then minus 9 x to the 9/7 when I've added 1 divided by 9/7 plus c. And let's just move a little more quickly here. That simplifies to 6 x to the 7/6 minus 7 x to the 9/7 plus c. Okay, that's it. Number 24. The following integral may be solved using substitution. So we're going to have to find the proper u that will make this work. And looks like that's the whole problem. Yeah. When I picked this, I thought that we'd be actually solving the integral, but now it's just finding u and du. Okay, so our proper u, well, you want to look for a good quote unquote inside function. I've got an x to the 6 inside this e. So let's try u equals x to the 6th. All right, the point is making a simpler integral. Right, that's why we do this. So I'm going to turn that e to the x to the 6th, a pretty nasty thing, into just e to the u. So that's the benefit of this u substitution. And this will work well because this means that du is the derivative 6 x to the 5th dx. So you take the derivative of u, then times dx. But notice here they've provided the dx for you. So you would just need to type in the 6 x to the 5th. And u equals x to the 6th. That'll work because that will turn, notice we have a 6 x to the 5th sitting in there already. So 6 x to the 5th dx, that's the same thing as du. So that'll transform my integral into e to the u du. And then that's not difficult to solve. But I won't go any further because the problem's not asking for it. All right, last page. The other pages on there are the answer key. All right. Again, a substitution problem. We're actually finishing the integral this time. Well, I think this expression here inside the parentheses looks like a good inside function, so a good candidate for you. Let's try it. Sometimes there's a little bit of trial and error to this stuff. Du is the derivative of u, 8x plus 36, and then dx. Okay, will this work? Well, what will happen to the integral now? Write it over here. Well, the denominator is in good shape now, just u cubed. and we'll have some sort of du over here. But notice that I haven't yet really dealt with that 2x plus 9, unless you notice that this here is just a multiple of that. If I factor out a 4, excuse me, that's then 2x plus 9. So there's basically just an extra times 4 here. Well, 2x plus 9 dx, that's what we actually have in our integral. That's what we need to replace. So I want to move this 4 on over. So 2x plus 9 dx, what actually shows up in the integral is 1/4 du. I just divided the sides by 4. So du divided by 4. So now we replace this with 1/4 du. So here's du. And let's just put the 1/4 outside. We can do that. And I'll go ahead and rewrite this 1 over u cubed as u to the negative 3, same thing. But this is easier to take an antiderivative of. So 1/4 times u. Okay, I add 1, that's negative 2. Divide by negative 2 and plus c. So that simplifies to, I'm just going to put the negative up here because I can. And I'm going to move this u down since it's a negative exponent. So that'll be a u squared down here. And still have 4 times 2, 8. So I'm just making it look a little nicer. Then, at the very end, now that we're at this point, I want to be back in terms of my original variable, x. So I replace u with 4x squared plus 36x. So 4x squared plus 36x, all that squared, plus c. And yep, that's the right answer. All right, now we're on to definite integrals. That's finding area under a curve. So it's an integral, but you have these bounds of integration, x between 0 and 5. Well, by the fundamental theorem of calculus, I can solve this by finding the antiderivative and then evaluating at those endpoints. So take the antiderivative, that's 5x cubed over 3. Excuse me, that's minus 4x squared over 2 plus 8x, and evaluated between 0 and 5. Remember here, you don't need the plus c because this is a definite integral. The plus c will just cancel out anyway. So the way you do this, you evaluate at the top endpoint, then minus plugging in the bottom endpoint. So we plug in 5. That's 5 times 5 cubed. That's not too nice. Over 3. Oh, yeah, it looks like it is going to be kind of a rough answer here. Okay, so here, these cancel a bit to 2x squared, or that's minus 2. So minus 2, 5 squared, plus 8 times 5. Now notice that when I plug in 0 for this, it's just all going to be 0. But you have to be careful with that because sometimes you might get tempted to say it's all 0, but it's not. Like, for example, if I have e to the x in there, then e to the 0 is actually 1. So just be careful. This is a polynomial, so yeah, if you plug in 0 for x, since you don't have a constant term, you're going to get 0. But just check that. Okay, so we will need a common denominator. So 5 to the 4th. I actually can't do that in my head, I don't think. 5 cubed is 125. And I would rather not spend time trying to figure all that out. So 125 times 5, that is 625. 625 over 3. This is 25 times 2, so that's 50, minus 50, plus 40. So, of course, these make negative 10. 625 over 3 minus 10. Well, we would like to find a common denominator. So rewrite 10 as 30 over 3. And then we can put all that together. So if you subtract 30 out of 625, you get 595 over 3. And yes, that is the correct answer. That's exact. All right, next, evaluate the definite integral. So because I have this whole expression inside the square root, this is going to be a substitution problem. So I want to make u that expression inside the square root. Du is 8 dt. Okay. And all right. So what happens now? Well, we've taken care of the square root part very well. That's just going to be the square root of u when we substitute over. Well, du, yeah, my eyes are not failing me here. That's correct. Okay, du is 8 dt. Well, what we have in the real integral is 3 dt. So I want that reflected here. So what is 3 dt equal to? Well, we'll just have to do a little algebra to figure that out. Let's see, that will be 3/8, I believe. Excuse me, du. Yes. So the way I did this was I really did an in-between step here. So I want 3 dt because that's what actually shows up in the real thing. Right? So how do we get there? Well, you could do an in-between step where you first get dt by itself. So 1/8 du. And then just multiply both sides by 3. So 3 dt is 3/8 du. All right, I'm a little skeptical this looks like it's going to be weird. I haven't done this beforehand, so see how it goes. All right, so 3 dt gets replaced by 3/8 du. So we've got 3/8 integral square root of u, or u to the 1/2, du. But be careful. With these substitution problems, you cannot just reuse the same old bounds because, well, up here, we're saying that this is t equals 0 and t equals 3. Well, we've switched over to a new variable, u, so we have to account for that. Well, you find your new bounds by plugging in the old t values into u. So I would write it as like u of 0, because t equals 0, that's the lower bound. Right, plug that into u, we get 1. So that is my lower u bound for my new integral. And all right, we plug in t equals 3, figure out what that is in terms of u. So that is 8 times 3 plus 1, that's 24, plus 1, 25. Okay, so 3/8, I'll just section that off to the side here. Antiderivative is u to the 3/2 over 3/2 from 1 to 25. Well, I can move this divided by 3/2 out, and sure, some cancellation will happen here. So 3/8 times 2/3, and then u to the 3/2 from 1 to 25. Okay, threes cancel. And get a little canceling here. It's just 1/4 left. So 1/4 times 25 to the 3/2 minus 1 to the 3/2. 1 to the 3/2 is just 1. So nothing to do there really. But this 25 part, well, think of it as like this. You do the 1/2 first. Okay, I guess I don't need those. 25 to the 1/2 to the third minus 1. So why did I do that? Well, by exponent rules, when you have a power to a power, you multiply those. So that would get me back here to 3/2. And I want it to be this way because first 25 to the 1/2 is nice. That's just square root of 25. Right? So 5 cubed minus 1. 5 cubed is 125. So 1/4 of 124. And okay, that probably is a good answer. Should be, let's see, let me check here. Should be 31. Yeah, I'm pretty sure that's right. Let me just double check. Yep, 31. Cool, we did it. 31. Just had to go over a couple spaces here. So I'm going to have to erase this stuff. But you can, again, you can look back if you need to. Okay, good enough. 3 problems left. Well, this is another U substitution because we have this expression inside a cubed. So we'll want to make that nicer. U equals 5y to the 8th minus 6. That'll turn this whole, well, this part into U cubed. That's easier to integrate. Du is antiderivative, or excuse me, derivative, sorry. I've been at this a while here. The derivative, yes, that's right. Okay, dy. So, this one actually looks easier than the previous one because what's truly in the integral, y to the 7th dy. Okay, so I don't really want to have this 40, at least not on this side. Y to the 7th dy is 1/40th du. So that means I replace y to the 7th dy with 1/40 du. So over here, we get 1/40th out, just put it out front. U cubed du, that is. And the only thing that's left is the bounds, the limits of integration. So -1 is my lower y bound. So let's write this here, u of -1. So 5 times -1 to the 8th minus 6. Well, -1 to the 8th is 1 because it's an even exponent. So that's 5 minus 6, -1. Oh, that's cool. Didn't change. So my lower bound is still -1, just u equals -1. And 0, that will change here. If you plug in 0, you get 5 times 0 to the 8th minus 6. So it's going to be minus 6. That's my upper bound, even though it's a smaller number than -1, because 0 was my upper bound. Hold on here. Oh, okay. I think I can see how this will work out. I see it's supposed to be a positive answer. I'm looking at the answer key. I think I see, yeah, I see how that'll, I think. Let's just keep going because I don't see a mistake that I made. All right, 1/4 u to the 4th from -1 to -6. Okay. Oh, yeah. Okay. Notice that this is a u to the 4th here. So those negatives, when we plug those in, they're not going to mean anything. Okay. So 1/40th times 1/4. So -6 to the 4th minus -1 to the 4th. Okay. Might need our calculator to help us with this a little bit. So, yeah, I'm not seeing a good simplification just yet. That's 1/160. 6 to the 4th. I think I'll need to type that in. Yeah. All right, that is 1296. And this is minus positive 1. So 1295 over 160. Okay, they do want us to simplify. Well, I can tell that it can be simplified because they're both multiples of 5. You can tell just by looking at them. So I would divide both by 5. So 1295 divided by 5 is 259. And 160 divided by 5 is 32. And that is the answer. It's in the answer key. So the simplifying was a little harder in this one, but the setup was easier than in the previous problem. All right. Yeah, you could check. You can see, like, how do I know that I don't need to simplify any more than this? Well, 259 is an odd number, and 32 is literally 2 to the fifth. So just 2 times 2 times 2 times 2 times 2. So 259 is not divisible by 2. That means there's nothing we can do to cancel anymore. All right, we've got 2 problems left. I wasn't sure that I would work through the whole thing, but here we are, home stretch. Okay, they're both area between two curves, so that's the recent content. Find the area between the following curves. All right, so in this first one, it's all nice and laid out for us. We've got our x bounds, we're between -3 and 1. So between -3 and 1. And, well, which curve is higher and which curve is lower? Well, I think I got a little ahead of myself here because it's going to depend. Again, I didn't do this one ahead of time. It's going to depend because these will cross each other at some point in that interval. Let's check. So x cubed plus 1 set equal to 0. Okay, subtract 1 from both sides. And if you take the cube root, you can do that. The cube root of -1 is still -1. So that means they cross when x is -1. That means that one of the curves was lower first, but then it becomes higher. In other words, we're going to need two separate integrals here because in these area between curves problems, it's always high function minus low function. So, which one is higher when? Well, in this case, it might help just to graph, as this is just the graph of x cubed raised up 1 unit. So it's just, normally this would happen at the origin. Y equals 0, that is the x axis itself. So we know this is happening at -1. So -3 is somewhere out here. So that means my high point, my high curve is 0, the x axis. But then on the other side, Now between -1 and 1, that polynomial is higher than y equals 0. So if you are not able to come up with a picture like this, you could just plug in some points to see which gives you the bigger value between the two functions. Right, so between -3 and -1, 0 is the high curve minus the whole x cubed plus 1 dx. That gives me this area right here. Then plus integral from, -1 to 1. Now x cubed plus 1 is the high curve minus 0. Right, how about I clear up this space now? Right, let's clean up these integrals real quick. From -3 to -1, there'll be a negative x cubed minus 1. Distribute that negative dx. Then from -1 to 1, just x cubed plus 1 dx. So I just clean those up a little bit. All right, so now let's take the antiderivatives. I'm going to need some space. Let's go over here. So we get -1/4 x to the 4th minus x from -3 to -1. Then we've got 1/4 x to the 4th plus x from -1 to 1. All right, so plugging in -1 first, right, I get -1/4 times 1. It's an even power. Then minus -1, so plus 1. Right, I'm not showing quite as much work as I might have before. Now, -3, we plug in. It's minus that. So -1/4, -3 to the 4 is going to be a positive 81. Think 9 squared. I'm not done yet. And that's minus -3. So plus 3. All right. Now, this one over here, I plug in 1 first. Then minus, if you plug in -1, this will still be a 1/4. And then minus 1. Okay, now we need to simplify. So these, no. This will become, with that negative outside, that'll be a positive 81/4. Let's write that. 81/4 minus this 1/4 out front here. Those come together very nicely. Then I'm going to have a plus 1, then minus 3. So minus 2 overall. Now on this half over here, notice I have 1/4 and minus 1/4. They cancel. But here I have a 1 and a double negative. So that's a plus 1, plus 2 for that right integral there. Well, look, those cancel. And I'm left with 81 minus 1 over 4. That's 80/4, 20. Nice, clean answer, 20. Okay. I'm glad to be done with that one. Number 30. This time we're not given as much stuff, and pardon my erasing here. So we're not quite given as much info, in particular the x bounds, but we'll notice that we're going to have a parabola and a line 18x that has a y-intercept of 0, and it's pretty steep positive slope. So we're talking about something like that. So the line is always on top on our interval, and the parabola is on the bottom. We need to find those points of intersection. That's where we're integrating between. Those are the x bounds. Well, we can clearly see the left one is 0, but the other one not as clear. So we set them equal to find that point of intersection. And these work best if you move everything over to one side. Then I could factor out x. So there, x equals 0, and 18 is the other one. Those are the numbers that we are integrating between. So 0 to 18. And I'm writing the 18x first because it's on top, on this interval at least. The line is higher than the parabola. And now we're just ready to solve. Right? So antiderivative, that's 18 x squared divided by 2, x cubed divided by 3, right, from 0 to 18. So why don't I simplify this part right now while we're here? This is a 9x squared. So we might want our calculator with this. These are kind of big numbers. So minus 18 cubed over 3. Well, then minus, plug in 0. Well, we can see that that'll just give us 0 in both cases. So we don't need to worry about that too much. Okay. Trying to look for anything nice here. Yeah, so I think I'll just want to type these into the calculator. So 9 times 18 squared that is 2,916. Then 18 cubed, excuse me, minus. Now, is that divisible by 3? Yes, great. So 18 cubed divided by 3 is a nice clean number, 1944. So now we subtract those, so 2,916 minus 1944, 972. And yes, that is the answer in the answer key. All right, there is the exam. Practice test, that is. The real exam will be somewhat similar, pretty similar, just perhaps some minor tweaks. So you will have 2 hours yourself for the exam. Right? Happy studying.